A modern city operates on a massive scale of human infrastructure, which is built from thousands of interlocking materials. Yet many of these systems rely on the same overlooked element. In the early 1800s, the scientific community was engaged in a race to categorize the building blocks of the physical world. In 1808, researchers isolated a new element from the common mineral borax. They named it boron. At the time, the discovery lacked the immediate industrial appeal of metals like iron or copper, which could be forged into tools and machinery. Researchers focused on materials that could stand alone as primary builders. They were not yet looking for a substance that provides value by altering the properties of the elements around it. On the periodic table, boron sits on the dividing line between metals and nonmetals, classifying it as a metalloid. This placement allows boron to form covalent bonds that modify the physical behavior of other substances, addressing specific vulnerabilities in their molecular structures. While metals like iron form the rigid frames of our structures, boron provides the chemical reinforcement that prevents those systems from failing. This bonding versatility allows the element to move between diverse applications, from agricultural biology to advanced defense systems. The element rarely serves as a primary structural material. Instead, it provides the necessary stability for the substances that build our infrastructure. Global agriculture functions at an industrial scale, moving millions of tons of produce. At the center of this harvest is a specific microscopic transport process. Within these crops, boron is responsible for the cross-linking of cell wall polymers, creating the structural pathways required to move nutrients to the flowering seeds. Crops deprived of this element suffer from cellular malformation, resulting in stunted growth and the failure of seed production. To maintain these yields, modern farming utilizes fertilizers containing boron compounds to ensure soil health across thousands of acres. Without this chemical interaction to hold plant cells together, global food production would face immediate and widespread declines. This same principle of material reinforcement is found in the manufacturing of the specialized glass used in modern industry. By infusing ordinary glass with boron, manufacturers create borosilicate glass, which resists cracking when exposed to the high temperatures of a laboratory. This chemistry enables kitchenware to move between the heat of an oven and the cold of a countertop without breaking from thermal shock. In consumer electronics, boron compounds are utilized in the production of thin, durable glass designed to resist a shatter when dropped. Boron is also used in the fabrication of semiconductors, helping to regulate the electrical performance of the microchips inside our computers. Without these thermal and physical enhancements, the glass in our pockets and the silicon in our computers would fail under the heat and friction of daily operation. When materials are required for extreme environments, engineers utilize boron carbide, a compound that ranks among the hardest man-made substances. Boron carbide's ability to dissipate the energy of a high-velocity impact makes it a standard component in modern ballistic armor. This combination of hardness and low density also makes the material useful in aerospace engineering, where every ounce of weight saved is critical. To reach orbit, rockets must shed maximum weight while resisting intense atmospheric friction. Boron-infused materials keep the hull lightweight without buckling under these forces. Human expansion into space and defense against extreme physical threats are made possible by the strength of these specialized compounds. Today, researchers are applying the element's properties to the challenge of clean energy storage. Modern batteries face a physical limit. As energy density increases, so does the risk of the internal components overheating. New battery designs incorporate boron into the cathode structure, regulating the flow of ions to prevent the heat buildup that leads to failure. A similar function is performed in nuclear reactors, where the element is used in control rods to absorb neutrons and maintain a stable energy output. The materials that sustain our cities, technology, and energy grids are not always the most famous. Many of them perform their most important work by improving the substances we use every day.